It's been tough. Raising my children after the loss of their father, the love of my life, my husband, Renee. And at the same time, I didn't want to just sit around and be sad. So I decided to hit the road and do what I love.
Tell me.
What was that?
So we're going to start up in about a minute or so. Hopefully your day is going well. Do any of you have like non-statistics related questions, comments, opinions? Joke that's appropriate? Okay, it's 10 after. Gotta say, I did my best to put you all into lab groups. And I did that based on the time slots that you signed up in. Not all of you did sign up for a particular time slot. So I put I won't say the leftovers, but there's a group of, I think, about 5 of you who are in one lab group because I have no clue the time slots that would work well for you. I also noticed there were a couple names of people who signed up for the labs who were not officially in Canvas, and so I added a couple names for that reason to Canvas. So you should have a Canvas invite if you're one of those folks. And there are a couple people who are sort of hard to place, and so it may require 1 or 2 of you to be a little flexible with your time frames. Time frames. Okay, that's how to pluralize it. I would suggest though, one of you is someone who said, "Oh yeah, I've got this schedule such that really until 8 p.m. I can't do anything." And so if you're in the group with the person who says, "Hey, I could start at 8 p.m." Be flexible. That would be appreciated by me. I'm sure others as well. Okay. Like I said yesterday, it's always good to start tackling questions that students might have. And I usually like to do administrative sort of questions first and then subject matter questions before we sort of get into new content. Today, we should be finishing up chapter 1, section 2, and then going into chapter 1, sections 3 and 4 as well. But finishing 1.2 first is on my schedule. But first questions that you might have. I know I did have a really good email question, but I'm hoping you'll just, as a group, come up with 1 question, 2, 3.
Yes, Professor, I have a question about the exams.
Yeah, do them.
So during the 24 or whatever hour period, is it like we have 1 hour within that?
Yeah.
Okay.
I'll set it up for a 50-minute exam. So literally it's 50 minutes to take the test, plus 5 minutes to deal with, downloading a data set if you want to do that. And then make sure that you scan somehow and convert into PDF form your notes that you want me to see to answer the questions, or heck, if you have 5 pages as you just write really big on blank paper, hey, that's fine too. But an extra 5 minutes should allow anyone to sort of take pictures of 5 pages or scan and upload. And so it'll be like 50-minute tests. Make sure that you have the time to do the uploading at the end. And it's any time window that you want, but it will be consecutive. So you can't like take a break halfway through and go go smoke a cigarette or something, and then come back to it. That's just not going to work.
Okay, thank you.
Yeah. Other questions?
Where do you see what a lab group you got assigned?
Yeah, that should be lab assignment 1 or lab 1 that I'm going to show you in a little bit how to get there. But the lab groups are assigned there, and I will if by the time we get to the end of the 12 to 1 window, if at 11:58, no, 12:58, one of you says, hey, I can't find my lab group, I'll try and walk you through that. But most of you will have naturally sort of clicked your way into the lab. You'll see that. Or if you click on the people tab, you should see lab group 1, and you could get a sense for who else is in your group. But as long as we're talking about the labs now, the way it usually works really well is once you get into the lab assignment, one of the people in your group will download probably the Word doc version of it, convert it into a Google Doc. And I'm not saying this is what you have to do, but this is what has been most popular with students in the last
in progress.
2 or 3 years. And so it's just download your lab, one of you, and then share it with other people in your group. And if you have everyone's names, you should be able to access them through regular Cal Poly email, but you'll probably use Gmail or something comparable to sort of share the document so you can work on it together. And I believe about 2 years ago, students tended to open up a Zoom window and then sort of work, with the visual thing going on so they could chat out loud. Zoom might not be the only way to do that. Discord's pretty popular as well. I'm going to say I'll let you figure out that. And some lab groups have been very successful without actual talking out loud, but they're communicating via other methods, often just typing in the document, what do we put here? Or, hey, how about this? Stuff like that. So that should answer a couple questions. Okay, so the question that was emailed to me that I thought was really great. Okay, yeah, Jasmine, I'm glad you raised that issue. I did not assign you a particular time slot. I'm going to allow you the flexibility to figure out when you're going to want to do it. And usually it takes about an hour to tackle an entire lab assignment. And when you sort of chat with each other in that first meeting, even if it's just email, you're going to say, hey, when's good for you? And most of you are in the 3 to 5 window, as in you signed up for something 3 to 5, and I paired you up with others who said 3 to 5. 5 to 7 is a little less popular. 7 to 9 p.m. a little bit more popular. But whatever works for you. And again, with the exception of one group, everyone should have at least one common 2-hour block, which will work. Okay. Oh, the question that someone asked yesterday via email, and that was, with the homework problems, are we supposed to actually, do them by hand? Because some of these problems would take a long time. For example, oh shoot, I lost you. For example, let me start to share screen, and then I'll drag and drop. Share that desktop. Good, share. So if I was looking at a copy of our textbook, and I've got some of it here, I think problem out of chapter 1, section 2, I think problem 4 was assigned. So you're reading along, you're saying, boy, there's a lot of data values. And then they continue to fill like half of the next page or the next column. It seems as though that would be hard to do by hand. 2 years ago, I had some students who did that by hand, but one of the sort of zipped up files that I asked you or suggested you download was just data from our textbook in GMP format. And if I double click on that, it opens over here on a different screen, but it opens the data themselves, the exact values that you would see here in the data set. You can verify like 122.2, 124.2, 122.2, 124.2. Yeah, these are those same exact values, and there happen to just be an awful lot of them. Okay, drag it down. We can see, yeah, I don't want to by hand deal with this. But as we suggested yesterday, if I wanted to create a stem and leaf diagram with that, I could use analyze a distribution of what? Well, of that first column. You could also give it a fancy name instead of C1. You could call it, what is this? The data on tensile strength. You could call it tensile strength or tensile ultimate strength in KSI. You know, you could give a better title than column 1. But if I click OK, it sort of shows me some of the information I might want to see. But if I wanted, shoot, I would stack that up so I can see it better. But if I wanted to have a stem and leaf diagram, which I could then cut and paste into homework, I could perhaps create one by just saying turn on that stem and leaf diagram. So the stem and leaf diagram appears because we selected it. Darn, this is really hard. When it doesn't display the little red triangle is your friend, but I turned on stem and leaf. I could turn off the outlier box plot because we haven't defined what that thing is yet. And so you have with this little red triangle the ability to do all sorts of intriguing things that we will discuss as we go through the term. So stem and leaf, that is your friend, and 112 represents 122. So the lowest value is usually what they choose here. And you're thinking 148 or so is the highest value. Now notice that these values have been rounded a little bit. In our data set, the lowest value was not 122 exactly. Let me show you under quantiles. You could say the lowest one literally was 122.2. With the stem and leaf diagram, we always round to the level of the leaf. The stem are the major sources of variability. We see numbers that begin with, in our data set, like 120 up to 150. So the numbers should all begin with like a 12 or a 13, 14, or maybe even a 15, but we don't see it here. So the digits that don't vary a lot, the first a few digits will be the stems. And then each individual data point is a leaf digit, and we round to get those leaf digits if need be. So that may have answered more than one question, but you never know. Okay. Any other questions that you'd like to ask, administrative or subject matter wise? Okay, well, I'm going to open up a data set that I remember fondly from many years ago, and it's in the class data folder. If you downloaded that and you want to work along and you've got GMP installed. Oh, just a quick note. If I if you haven't installed GMP yet, it will be helpful for the lab. And excuse me, I based on a discussion with a student yesterday, I changed up what is written here. There was no tech support option. I sort of steered you the wrong direction because from Stat 312 a couple of years ago to Stat 312 now, we now have a software download channel. I don't know what a channel is, but you click on it and then you should go ahead and install version 16 or 17 more likely. And then the instructions here from Winter should be fine to grab onto the installation. Okay, so in our looking at the data, sort of problems assigned recently do include that problem 4, where maybe I would do a stem and leaf with the software. How would I create a histogram? How do I define a histogram? Here's where that data set that I was mentioning a little bit ago comes into play. It was a data set collected by a guy named Lowell Ballard. He is a graduate student in, sorry about the PDF access denied. I need to find that and fix it. The upshot is most of you can just click the download directly from the software download channel and it should work fine. But if you have questions, let me know. Lowell Ballard, a graduate student in biology at Virginia Commonwealth University, got a grant from the Department of Environmental Quality to go catfishing across the entire summer. And yeah, that now means something different than it did in 93 when he did this. He literally went and fished for catfish, and there were a variety of species of catfish. BCF for blue catfish is one of the varieties. And for each catfish, he recorded the length in millimeters of the catfish and then determined how many items were in the stomach. This is a catfish that just fed on something. I don't know what it was, but there were 45 of them. And the real question they had was, do some species of catfish tend to be more likely to eat American shad than other species of catfish? Long environmental question there. Really, let's just look at the lengths of the catfish in our data set. And I happen to be looking at or focusing on the blue catfish and then the channel catfish, two of the four varieties. White catfish, you can see WCF. It looks like it's got a which means essentially don't include this data point. And all of the white catfish were sort of excluded from our analyses. You can see that we're going to also ignore the species flathead catfish just to make it a little bit easier to deal with. If I were using analyzed distribution, okay, I could tell you I want to know about the lengths of the catfish, and I could do it separately for each of the two species. I want to do just the two, not all four species. It'll be easier to read. Usually inside JMP, the software is pretty straightforward. It actually reads like a sentence. How does the length vary between the species? Or can you show me how the length distribution changes between the species? And you see output that discusses or describes, well, I like to stack it up so I can see what's going on here. And we have different scales here for the blue catfish, 0 to 1200. And the channel catfish, it seems like we cap out a little bit lower. Maybe what I should do is make sure that the axes are sort of comparable so I can maybe see more carefully. Yeah, these guys are shorter than these ones. Now, admittedly, there's a lot of them here down below 200 millimeters. But in the channel catfish species, not many above 600, whereas in the blue catfish, quite a few above 600. Okay? I'm already interpreting this histogram in the way that you know I'm interpreting. It makes perfect sense. This histogram is basically a collection of boxes where the height corresponds to the proportion of the individuals in any given length category. So for example, if I hover over any of these boxes, and let's just try this guy here, 300 to 350, and I apologize if this is really a tiny font for you to see. If you're hovering yourself over your own little box, you can then see that it's a 300 up to, but not including 350 millimeters in length. And there's 396 of them, 396 of the 2644. We could even figure out what percent that is, or what proportion of your data set as a whole is in the 300 to 350 range. And the height corresponds to, actually, let me be more careful. With this particular book, the area corresponds to the proportion of the observations in this range. The fact that all of these individual blocks are exactly 50 units wide, it means the height is also proportional. And typically with a histogram, we do have software generating equal category widths. And so if I wanted to describe my species, blue catfish, in the lengths, I would say, well, there's no one below 50 millimeters. Okay, between 50 and 100, I got 47 of them. And then between 100 and 150, 157, etc. So I think that is pretty clear in some ways, but I'd love to pause and tackle questions if you have them about our catfish histogram. Okay, so what I'd like to do is to just note, I'm happy even if in 3 minutes your brain says, oh, I had a question and I haven't asked it yet. Just unmute, interrupt, and let me know you got a question. We can easily go back. That is really what I'd love to do. And so I'm not rushing. I'm just saying it seems like it's time to move on from what you've not said, or maybe you said something, but you didn't unmute first. So I'm going to be moving forward and moving forward and sort of tackling a hypothetical question. And the question is, what if instead of 50 millimeter wide categories, and that's like 2 inches, what if I went with 10 millimeter wide categories, 5 times as many blocks? Would the distribution change? Would the shape change? Probably not that much. Probably not that much. I can maybe even, if I can mouse over this, under our histogram options, shots percentage, set bin width. I can choose to have a bin width instead of 200 or 50, what we see. I could have a bin width of 10, like I suggested, 10 millimeters wide. The picture is still the same in shape. It just does seem as though it's a little bit lumpier or bumpier or a little bit more granular, if you will. And I could choose it to be even fewer categories. There's sort of a nice trade-off between the bin width and the shape of the picture. You can focus on fine points more easily with narrow bin widths. Okay, you can see that it sort of goes down and then up again more easily than if the bin widths are 50 units wide. But if you have bin widths that are too narrow, let's adjust that yet again. Rather than 10, let's go with a bin width of 2. That seems excessive. It's a little harder to read. In fact, it's very difficult to read where there is, like you can see none of them, but it's sort of hard to tell where things are set with 1 or 2 or 3. And so it's just a pain, okay? So you want to choose a bin width that matches the number of data points you have, and then information about the width or the range of the distribution. And so the software will usually choose something reasonable for you. But I will always recommend, as a professional statistician, I always recommend clients to choose a bin width that's narrower than the default option and choose one that's a little bit wider and reflect on all 3 histograms and say, well, which one gives me the most information that's helpful? And then maybe present that one moving forward, okay? But let's continue with our thought experiment and let's push a little bit further. What would happen if I saw bin widths that weren't 2 millimeters wide, but 1 millimeter wide or 1/10 of a millimeter wide? I mean, shoot, Lowell didn't measure the catfish lengths to the nearest 10th of a millimeter, but to be honest, could you? I mean, some of you are saying, well, it might be flopping around in the boat. Yeah, no, but if you had a really precise measuring device, could you measure something much more precisely than to the nearest millimeter? To the nearest 10th or 100th of a millimeter, I would imagine, would make some sense. And if we had not just 800 data points, but if we had 8,000 or 80,000, if we had more of the catfish in the entire population in our data set, and we had very narrow categories, I'm going to make the claim, like in your calculus class, that we end up with, right? Here we go. I'm going to make the claim, like in your calculus class, you would eventually see a very smooth curve, okay? And so what I want to do is sort of draw a distribution, basically think a continuous distribution, which is sort of like an extension of a histogram with narrower categories, but a very large number of observations. You would see that histogram has, in our case, sort of a shape like that, Okay. Now, you're sort of thinking, well, the histogram really does have these boxes or categories that you sampled from. And we did say, well, there's that one, then there's this one, then there's this one, and then there's that one. But if these categories got narrower and narrower, and yet again narrower, we would ultimately see the shape overall becoming like a continuous function, or perhaps maybe not a continuous function, but a function where again the area corresponds to 100%. So with this distribution here, and this is a continuous distribution, and by continuous distribution, well, that's contrasted with discrete distribution that we'll talk about in a little bit. But basically think, if you measured it more precisely, could you get a different number? If the answer is yes, you've got a continuous distribution. So things like a person's weight would be a continuous distribution, or the weight of a bolt would be following a continuous distribution. If you ask yourself about, like, how many siblings do I have, your answer is probably going to be an integer, or like half. I've heard a person mention a fourth of a brother, and I had to ask about that. It was like a dad married someone else before this kid was had, and that lady brought a stepchild to the marriage, which dad then adopted. And anyway, a fourth of a brother. Fine. The point is, with a discrete distribution, I could list off all of the possible values. Continuous distribution corresponds to situations where you really can't tell me every possible value that is possible if we simply measured more precisely. Okay. So in a continuous distribution like that, you could think of it as a limit of histogram as the category width approaches 0. Furthermore, for this continuous distribution, and maybe I'll put a y-axis here, and have the height f of x here for various values x. F of x is just the height, but we require for a continuous distribution the integral of f of x dx from negative infinity to positive infinity to equal exactly 1. One other thing that is necessary for continuous distribution. Here's one of the two things. Another is f of x is greater than or equal to 0 everywhere. So as long as you have these two situations satisfied, there's always a non-negative value for the height, okay? And the total area under the curve is exactly 1. You have a continuous distribution. And for continuous distributions, the area between a value, say A and B, okay, so integrating from A up to B, f of x dx, that's equal to the percent or the proportion between A and B. Now, some of you would say, hey, hold on, do you include A and B at the endpoint? Is A included in that range? Is B included? Are neither included? Are both? And the answer is, if it's continuous, I don't care. If it's continuous, you shouldn't care. Let's think about this distribution as the distribution of heights of everyone on the planet. Now, that's a large number of individuals. And let's just choose A to correspond to 175 centimeters exactly. Okay. And if I said, how many of you are between 175 and 195 centimeters, you can say, oh, okay, am I in the range? Yes or no. But if you're really close to 175 centimeters, I could always say, okay, measure yourself more precisely. If you're 175.1 centimeters, you're certainly in the category. But if you're 160, sorry, I said 175. And if you're 174.1 99, you are not in that category. Is there anyone who's exactly 175 centimeters right at that boundary? The answer is if you measure a person's height more precisely, they're either shorter or taller than 175. So there is no actual area directly above that 175. We only measure in between. And do you include the endpoints? It just don't matter. Okay, so let me make sure I take a screenshot of this so I can move forward and clear that. Any questions on that so far? Okay, so let's use a let's sort of discuss why you'd use these distributions. The real reason is if I showed you a histogram and I showed you a histogram for a second sample and a third and a fourth and a fifth, and if they all had certain similar characteristics, it might be useful to assume that the population that you're sampling from has those same characteristics, okay? And so let's talk about, excuse me, apologize. Let's talk about a uniform distribution, okay? So here's the uniform. And I'm going to say, okay, what if values in the range, and I'll go with a histogram, or I guess a distribution, between, say, 0 and 100. And uniform distribution basically says, okay, all of the possible values seem equally likely to be the observed value. And so there's a certain height here, and the spread has every single value equally likely, if you will. So our height of the density function, our distribution height, f of x, if it's just spread uniformly across the range 0 to 100, and we require that 1 to be equal to negative infinity to infinity of f of x dx. And if we're always 0 after 100 and always 0 before 0, okay, values below 0 are just not possible. Values above 100, not possible, okay? That's going to be integrating just 0 up to 100 f of x dx. And all of those f of x's are the same. So I guess if I wanted to work it backwards, let's use geometry. Oh, if the total area of this rectangle that it looks like it's forming, this total area here, if that is exactly 1, and it's 100 units wide, you're sort of thinking, okay, any individual value has to be exactly 1 over 100. So I could write f of x equal to 1 over 100 for 0 in the x to 100 range. And notice that I have less than, okay? 0 is less than x, less than 100. If I put 0 less than or equal to x, and then x less than or equal to 100, it would still be the exact same. Again, continuous. We don't care about those end points at all. So if we're in the range 0 to 100, there's a certain possibility, okay? And otherwise, it's just not going to happen. So OW for otherwise. So in the 0 to 100 range, there's the same rate of occurrence in any one unit wide area. And in any 5 unit wide area, whatever 5 unit wide area you choose from, it's going to have the exact same, exact same, apologize. The exact same area, okay? So with this uniform distribution here, we could talk about what is the chance that a random variable, so if I'm going to pick something from this 0 to 100 range, what's the chance that it's less than, let's say, 30, okay? To find the area of 30 or less, okay, that would correspond to the chance, and let's find there's 50, there's 30 here-ish, 30. So 0 up to 30, that is the probability that the random variable x is in the range 0 up to 30. Okay. And I'm trying to not be fussy about it too much, but you might be careful. Capital X is the way our author refers to a random choice from the distribution. A lowercase x, like over here or there, is a possible value. So the chance that you're in the 0 to 30 range, all we need to do is to integrate from negative infinity up to the upper end of that range, 30, f of x dx. And in this case, I know f of x right there. And so that's just integrating from 0 up to 30, 1 over 100 dx. And most of you could do this in your head. But I'm going to say, does it look like 30% overall? That's going to give you a 0.3. I'm skipping the integration itself, but I guess I could have x over 100 evaluated, x being 0 and 30, and do the subtraction. So there's a 30% chance, if you will, that a random number from the range 0 to 100 is going to be in the 30 or less range. There's also a chance of 30% that it's going to be strictly less than 30 in value. Again, excuse me. Again, the chance at exactly 30 is negligible, so we ignore that. Okay, again, grab a screenshot and let's clear and move forward. Because there are some distributions like the uniform that happen over and over and over again. One of them is the exponential distribution, and another is the normal distribution. Chapter 1, section 3 is exponential, and chapter 1, section 4 will cover the normal distribution. So for the exponential distribution, let's write that one out. And there's some cool facts about the exponential distribution that you'll discover in the context of the lab activity, but they're also cross-referenced with our textbook. But the lab activity walks you through how to create random data from JMP, and then you could look at the histogram and see what you think about it, what it looks like, etc., the histogram. But for the exponential distribution, our density, our probability distribution, is going to be always lambda times e to the minus lambda x. For x's, they're at least 0 in value. And I guess lambda also has to be positive. And 0 for pretty much everywhere else. Otherwise, you could say x being less than 0. Okay. Okay, so there we go. What's the shape of this distribution? Well, I'm going to sketch it out for you, but you'll explore it again in the context of the lab activity. But here is your shape. If I plotted f of x, okay, for various different values, lowercase x, you're going to see this exponential distribution is always going down, and is going down at a lower and lower rate. And shoot, I need to, darn it, I erased the wrong thing. Okay, well, nope. Yeah, I did that. Okay. Okay, I'm annoyed that I can't erase just a portion of it. Oh, well, we're going to sort of just go with it. So how do we deal with this overall distribution? Well, you'd say values close to 0 are pretty darn likely, but values that are very large, possible, but far less likely, okay? A friend of ours that we want to discuss is the CDF, short for cumulative distribution function. CDF, cumulative distribution function. The CDF is given to us as capital F of x And that is integrating negative infinity up to lowercase x f of y dy. Let me show you that in picture form instead, okay? And let's go with pink here for a value of x less than some a. The CDF is exactly that shaded area. So just integrate. Just integrate. And that is a fairly easy thing to do. Let me let's do a screenshot here. Then I'm, oh, hold on. Let me, okay. Let me do a screenshot now. And then I'm going to choose to erase some of the stuff upstairs and work out what the CDF is. And some of you have already gotten to the point or the conclusion of that one, but let's go ahead and use the magic erase. Okay, come on, erase. Okay, pencil only and erase. Okay, hold on. Are we doing the erasing? Here we go, erase. Okay, so let's just erase with a touch. Okay, that's not doing it. Great question. I can see that here. Lambda is just a, if you will, a parameter that is undescribed so far, but lambda is related to the average value of all things, okay? Lambda is not the average itself necessarily, but it would be related to the average, and it is related to the rate of decay. You can see that minus lambda times x, the larger, oh man, my pencil is off today. Okay, so you'd say the larger x is, because lambda is greater than 0, it's strictly positive. The larger x is, the further out into that tail you're going to be, you know, x being large, out, e to the minus, well, big, okay? And so if lambda was a larger value, just as it pushes it further out, okay? So it pushes things further out, or if lambda is small, it pulls it right in, okay? Okay, so I unfortunately have to clear that whole thing, and we're going to, darn it. I'm wondering if there's a problem with my pencil here. Darn it, okay, so let's switch over to touch and, okay, so I have lost complete control of this little device that I'm using to draw with, and I apologize for that. Let's see if I could try one more time. Okay, so it is unclear to me how I should. Okay. Okay, so the device I have used for writing or have to use with this is not responsive, and that is annoying for me. And looking at the 151. Okay, so what I'm going to do is just go ahead and leave the meeting and join the meeting again and start sharing one more time or copying. And ooh, hold on. I know what I'm going to do. I'm going to stop sharing and reshare. That will be perhaps quite helpful. Okay, desktop. Here we go. Share. Okay, so I'm hoping that, sorry, I'm hoping I have the ability to draw now, and we'll find out. Okay, so we've got our exponential distribution. Yay. And the I see there's only one I. You know what? If I weren't OCD in some ways, it would be certainly easier. The exponential distribution here. And again, f of x is just e lambda e to the minus lambda x, or 0 for x greater than or equal to 0 and x less than 0. And again, lambda is positive, okay? So we know the CDF capital F of X is integrating from negative infinity up to X F of Y dy. Okay. So let's go ahead and do that integration right now. Okay. So and again, our picture suggested we want to, integrate up to some value A. How would I do this? So F of A is, well, I have to integrate from 0 up to A. So that's integrating 0 up to A, F of Y dy. And that would be then integrating 0 up to A, lambda e to the minus lambda x, lambda y dy. And that's just 1 minus e to the minus lambda, apologize, minus lambda y, evaluated at y being 0 and then x. Okay. So this is going to be just 1 minus e to the minus lambda times x minus 1 minus e to the, well, lambda times 0, lambda times 0, that's, well, that's just going to be canceled out because that's just drops out entirely. So we have e to the minus lambda x. Okay. So yeah, literally the CDF is e to the minus lambda times x. And so for any value that I plug in here, and I'm sorry, I should have a in that spot, and a in that spot, and a here in that spot. Okay. So for any particular value, the lower tail area, okay, is fairly quick to calculate. Damn it. Yeah. I'm sorry. Oh, no. That's a 1 minus. There's the 1 from there. 1 minus. Okay, there we go. That's what was looking wrong to me. Okay. So with functions that you can deal with, polynomials, rectangles, easy to do. Okay. What about if we moved on into other shapes? And there's one that is really key for statistics, and that is the normal curve. Let me show you what the normal curve looks like. And I'm going to sort of say, you know what? It's not overwhelming because software will do it for you. Okay, so let's cancel that. Okay, normal curve overall. And so the distribution for the normal curve, the density f of x is just integrating. No, I'm sorry. F of x is just 1 over the root of 2 pi, okay, times sigma in the denominator, but not within the root, times e to the minus 1/2, okay, x minus mu squared over sigma squared. And you're sort of thinking, I don't want to deal with that. And I don't either. Just note that mu is the center value. And sigma is related to the spread. And we're going to note later that mu happens to be the mean of the population. And sigma is the standard deviation. And I sort of quickly want to show you how to sort of think this through with this thing called the empirical rule. The empirical rule, empirical means related to observed data. This is just something that for this distribution, we see over and over and over again, the same sort of pattern. And in the range mu plus or minus 2 sigma, so going out 2 sigma, and in either direction, mu minus 2 sigma and mu plus 2 sigma, that's going to be about 95% of the values, 95% of the area under the curve is in that range. Part of the empirical rule. If I go up and down only one sigma, so mu minus sigma and mu plus sigma, that range in the middling range there, that's about 68% of the values. And if I go mu plus or minus 3 sigma, that seems like a quite wide range, mu minus 3 sigma and mu plus 3 sigma. We're going to see nearly 100%, well, 99.7% or so of the values will be in that range. So it's fairly quick if I tell you just the central value and then a measure of the spread to be able to get a sense for what the shape of the distribution looks like. So I'm going to describe a data set that we can conceive of. The heights of adult male Californians, I'll tell you that mu is 70 inches and sigma is 2.5 inches. They happen to be really close to the truth, and rounding is always easier. And what I always like to do to draw a normal curve is I just draw a curve that looks bell-shaped approximately. I'm going to label the central value, here in this case 70, and then I'll chop off a couple percent at each the bottom and the top end symmetrically. So it looks like I've chopped off about 5%. And the empirical rule says, well, twice the standard deviation is how much you go down and up. So 65 to 75 inches is the range of heights of about 95% of adult males. Okay. So that's not so hard to work with. The question is, if I ask the question, 68 inches or less, how do I figure out that shaded area? I guess I could integrate, but I don't want to have to do that. What I want to do is to rephrase my question. Instead of using the inches ruler, I want to convert into a ruler that I'll call the Z units, or the number of standard deviations above average. And I know I got about 30 seconds to go, but I'm going to say it's just a way of rescaling things. 68 inches minus the average 70 inches over the standard deviation of 2.5 inches. That just says negative 2 over 2.5, negative 0.8, okay? Negative 0.8 standard deviations above average. And if I tell you individual is 0.8 standard deviations below average, that alone should be sufficient to figure out exactly what percent of individuals are at that height or less. Now, our book has a table in the back of it that I don't love, but JMP has a probability distribution calculator that the lab today walks you through using, so you could find the area, what percent of individuals are 5'8" or shorter of the population who are presumed normal with mean 70 and standard deviation 2.5. So because I say that I'm going to be stopping every day right on the hour and I feel like I went over by a minute, I apologize. I'm going to stop the recording and